fun time again.
Hi, Professor.
Yes.
Before we begin, I have some questions. Can I
Is
ask?
that Sanyam?
Yes, yes.
Uh, yeah, no, I'm just thinking whether you should ask now or maybe in 5 minutes because there will have more people joined in by then.
Okay, okay, sure. That will be
Just
perfect.
let's do maybe in 10 minutes. We'll have some more people in the class.
Okay,
Huh.
okay, fine.
Yeah, no, I appreciate your question. So we'll just start.
Thank you.
Where are you right now, Sanyam?
Sorry, what?
Where are you based right now?
In Mumbai.
In Mumbai. I see.
Yeah.
ठीक है. Chalo, we'll just take up in a few minutes. Okay, so let's see where we were. We were at this, right? Let's just start from here. Level crossing probability, right? So we had this. Okay, let's start from here. Uh, so we have a simple symmetric random walk, takes +1, -1 values at each step, each with probability half. We're asking the chance of its hitting A or -B, right? Which one does it hit first? It's a level crossing probability. There are two levels, right? So we want to find this probability. And we observe that the stopped process is observed at minimum of n and the stopping time is a martingale. And this is since the probability of stopping uh, is finite almost surely, hence, by the way, can one construct a path where it's not going to stop? Up, down, up, down, up, down forever, right? So yeah. So S min tau is going to converge to S tau almost surely. It's a bounded random sequence of random variables. So you have bound convergence theorem, which tells you that E of Sn min tau is going to converge to E of S tau. E of Sn min tau, because it's a martingale, is just equal to E of S0, which is 0. Right? So E of S tau then becomes 0, which means A times probability that S tau is equal to A minus B times probability that S tau is equal to minus B is equal to 0. And that then gives you an intuitively plausible probability right here. That's what we saw last time. And now we'll ask ourselves, so this is where we were last time. Any questions on this? Salim, go ahead. Let's talk about your questions now. You can unmute. Yeah.
Okay. So first question is related to the martingale transform, which we have covered last time. There were two things. One is a predictable process, Cn, and the martingale process, Mn. So we have associated intuitive explanations behind these quantities. Cn is kind of a amount that we bid in the nth game. And the difference between Mn and Mn minus 1 is the winnings that is generated from the nth game.
Just
So,
give me 1 second, Salim. Let me just make sure I have the. Yeah. Okay. Go ahead now. Carry on.
okay, so we have associated intuitive meanings with the Cn and the Mn. Cn being an predictable process and Mn being a martingale process.
Adapted process. Yeah.
Yeah,
Martin.
yes. But with the Yn, do we have any such intuitive meaning, or it is just a mechanical example that we have created to explain this martingale transform concept?
Yeah, we went to great pains to explain that Yn is an extremely profound quantity, right? You're in a gambling casino, and what you win is, and this is one of those unique casinos where the winnings in any game is fair game. So on an average, it's 0. It's a fair game. And this is the amount you bet, CK, right? So at time K minus 1, you decide how much you're going to bet on the game K.
Yes.
So CK, you decide then MK minus is what you win in the casino in that
That's
game.
realized later. So that's a kind of exposed after the game, and CK is ex ante non.
The bet you make, yeah, and
Yes.
that's what you realize. And then if you sum up your winnings, that's Yn. Yn is the amount you've won in n steps, right?
Okay. The only part which is not clear is the multiplication between these CK. If Yn is the amount that we won in the n games, wouldn't that be I think that is how I understood it. The winnings from the n games is the total mn.
Y- No, it's why? I mean,
Th-
it's in case
because
the
that's why we are subtracting this mn minus 1 to have the winning from only the nth game.
no,
Uh,
no. This is if you bet 1 rupee, then your winning is mn minus one. If you bet cn rupees, then your winning is cn.
okay, so these are kind of normalized
That,
quantities.
that's right. That's right.
Okay, okay, okay. This is clear.
Mm.
And then next question is related to the stopping time.
Mm-hmm.
Uh, in the stopping time, we have defined it as uh, basically the set of all observations such that the random time that we have defined tau being less than equals to n is fully determined by the information that we have up till the nth point. So
Right.
hence this is fn kind measurable event. Uh,
Not miserable. Not yet. It's measurable.
it's measurable, but if it is a stopping time, valid stopping time, then it is fn measurable, right?
Yeah. Yeah.
So we defined it as like tau less than equals to n.
Mm.
Will the definition change if we just keep tau equals to n?
Right. So let me ask you this. If indeed this property is true for all n, what can you say about tau omega equal to n? Sorry. Mm.
That is also fully determined uh, by the information that we have up till the nth time interval.
Well, isn't it the kind of uh, you know tau omega less than equal to n intersection with the complement of tau omega less than equal to n minus 1?
Yes, my question is, are they equivalent? The definition that we have clearly implies this,
Yeah,
but
that's right. That's where I'm going with this. So you agree that if indeed this set is in Fn,
then this one will be
then tau equal to n is also in Fn.
yes,
Have you
yes,
me for every n? So the other way around, which will may answer your question, are they equivalent or not, right? And the answer is
yes.
yes, they are equivalent. So if I tell you that this is true for every n, then is it true that this set is also in Fn
Okay, by the union,
by the union? Yeah.
finite union. Yes,
Right.
this
Right.
is okay.
So then why did we choose something as, kind of less intuitive as this quantity for definition and not the quantity that tau omega equal to n should be in Fn? Any idea? That's right. Just take a union of tau omega equal to m equal to 0 to n. That's also in Fn, right? Yeah. That's right. That's I'm using no, but I'm using that, right? I'm using that. Yeah, yeah. So I don't know. All I'm saying is that this event here is union of tau equal to m equal to 0 to n. Now all these guys are right. So my question now is why did I use this above definition and not the below one? It helps and proves. That's one answer. Uh-huh. But maybe now you need to broaden your kind of imagination and see what might the answer be. Yeah. Yeah. No, so that would come out easily even with tau omega equal to n definition. But to this generalize extends to continuous time. That one does not extend to continuous time. Tau omega equal to n, if n takes a continuum of values, then I'm taking a union of uncountable events, and then anything can happen. Yeah, all bets are off. Sets can be probability 0, the union can be probability 1. So yeah, so that's why this is the definition that's acceptable. Sanyam, any other questions?
Yes, one more question that's on the stopped process. We have kind of demonstrated the concept using this example only of the transformed martingale.
Mhm.
So on that, I just want to know, will we be proving the concept in more generality? What is the proper result related to that stopped process? Uh,
I mean, it's right now it's proved, right? It's done. They were,
but
there's
is
not,
this only, so the only question is, we have demonstrated the concept using this particular kind of a transformed martingale.
Yeah, yeah, this is a good way to show things.
Okay, so does that imply that it will hold in general as well, right?
General meaning what? It,
If
but in
uh,
continuous time you're saying, or in
in general, if there are, let's say, we
this
have,
is general. This is general result, right? M is any martingale. Stop process
yes.
also a martingale. That's what we've proven right now. Because Cn is now an indicator function, so it's obviously bounded. So no assumptions there, no extra conditions there on M. M just has to be a martingale, then stop process turns out to be a martingale. It's as clear as that. Only generality you can say is okay, what happens in continuous time?
What is the let me digress a little bit. What is the meaning associated with the stopped process?
I mean, stopped in the sense, you've taken you have a strategy that, okay, I am going to stop when my wealth becomes equal to 200 rupees, or when I've lost 100 rupees or more. That's when I'm going to stop. You have some conditionalities of when you're going to stop, but it's a random time, right?
Okay. Yes, yes. That
Random,
depends on which states are being transitioned in the process.
right. So this allows for the fact that if you've not reached the stopping time, then your process is still kind of, it's still evolving. Amendment tau.
Okay, so so if Mn is a martingale and there are well-defined kind of states or kind of some time point, not time points, but states where it can stop, then the stopped martingale is also a martingale.
Right. I mean, if there's a well-defined stopping time, then the stop martingale is also martingale.
Okay, okay.
Tau just
This
has stopping time, basically.
okay. This is clear. And just want to know if there are any references for these things where we can get more examples related to martingales.
I mean, if you want to fall in love with martingales, then the book is Probability and Martingales with David Williams.
Okay,
It's a lovely book. So I've given that as a reference, David Williams, Probability and Martingales. And your other question was about martingale convergence theorem.
yes,
Just see the proof of that. It's a beautiful proof. And it's given in this book. I'm not covering it in this course right now.
yes, yes, yes. And are there any specific uses of that martingale convergence theorem in the course forward?
In the course, I'm not sure right now.
Okay,
I don't think we'll use it much.
okay,
As such, it's a very powerful theorem. I mean, you get a two-line proof of law of large numbers, strong law of large numbers from it. Um, but yeah, I don't know if we'll use it very much in the course. I'll, rem-
okay,
but I mean, it could be that we do. So in which case, I'll refer to this.
sure. Thank you.
ठीक है सर, sure. Thanks for asking questions. Huh?
Yeah.
Yeah. All right, guys. So now our next question was E of tau, right? How do we find E of tau? Expected time. What do you think that's going to look like as a function of A and B? What happens if A increases? What should happen to E of tau? Should increase, right? What happens when B increases? Yeah. So then any conjecture on what it might look like? Should it be A plus B? That's as good a guess as any, right?
But then you also want to worry about A plus B is just to go all on the increase.
Yeah, yeah.
You know that it's a martingale, so
That's it's going to be more than A plus B for sure. But it's a good question to ask, to think yourself what might be a good conjecture for it. So the answer turns out to be, yeah, it's a beautiful answer, right? This is not as intuitive as the earlier one. This requires, and right now I know I had a good intuition for it, but right now I won't be, I didn't think about this, but it's E tau is A times B.
oh, this is exactly.
This is the answer, A times B. So now why do we say that there should be a good Markovian way of building this argument? I just don't recall it. Why it should be multiplicative, but it's worth kind of thinking about this. So what's the right way of looking at it that it immediately suggests itself? All right, but let's see how we do this. So this martingale now becomes useful. So often the problem in probability becomes finding the right martingale. You find the right martingale and you can say a lot about the system. Okay, so in this case, this is the martingale. Why is this? We showed this earlier. Because your xi, it was n times sigma square was the martingale. Sigma square is 1, yeah. Yeah, it's just plus 1 minus 1. Second moment is 1. Sigma square is 1. ठीक है? So now, again, the stop process is a martingale, and the stop process is going to converge to m of tau, right? Because tau is less than infinity. So n, as n increases on omega by omega, eventually n will exceed tau. So mn min tau will become equal to m tau and stop there. Now you can write that mn min tau, this quantity right here, evaluated at n min tau, is less than or equal to a square plus b square plus tau, right? Because Sn, all we are saying is Sn min tau square minus n min tau. We are trying to, actually this should be, yeah, that's fine. So certainly Sn min tau square is less than or equal to a square plus b square, right? It's less than, and then minus n min tau is less than plus tau. So we can use dominated convergence theorem, right? Because we have to bound this quantity right here to basically use dominated convergence theorem. We need to dominate it. So this is the dominant quantity. Let's assume that E of tau is finite. We expect that to be true, right? You're starting from 0. You stop when you either hit A or minus B. You expect that to happen in finite time.
Probability of infinite is zero.
That's right.
You're only giving positive mass to finite, so it must be finite.
Dekho, I can give you a random variable which is finite.
Because we earlier showed that probability of tau being infinity is zero.
Yeah. No, all I'm saying is, all I told you was that tau is a finite random variable. I didn't tell you that expectation of tau is finite.
Given the probability being not finite, the expectation being finite is much smaller than probability.
So, I mean, we've already discussed this before, but just to, bring out an interesting case, which if you studied Markov chains, you would have seen. The random walk that we are talking about is a symmetric random walk, goes up with probability half, comes down with probability half, right? What's the probability that starting at 0, you come back to 0? That's 1. How do you prove that? Huh? Law of large number, that's a reasonable proof, I guess. Yeah, I mean, it's a reasonable direction. It's not immediately implied by it. The law of large number is just telling you that Sn is going to remain Sn by n is going to remain close to 0. It requires a proof, right? And what's the expected time for it to come back to 0? That's infinity.
Because you don't have.
Because I mentioned this to you, yeah. So this is a fascinating example of a Markov chain because Sn is a Markov chain, right? Sn plus 1 just depends upon Sn, right? So it's a Markov chain. Now, if you study Markov chains, then you know that Markov chains can be transient, right? That is, they visit states only finitely often and then they get absorbed. Or in this case, for example, if your random walk xi had mean 0.75, like, it goes up with probability 0.75, goes down with probability 0.25, then intuitively you expect it to kind of blow up to infinity, right? After a while, it becomes bigger than any threshold you can come up with. So it's unbounded and going to infinity. Right? That's an example of a transient Markov chain. Right? On the other hand, this particular Markov chain, which I mentioned to you, is a recurrent Markov chain. Recurrent Markov chain. It visits each and every state infinitely often. But it's a null recurrent Markov chain in that the expected time to visit each and every state is infinity. So in stationarity, fraction of time you spend in any state is still 0. In the sense that if the expected time to visit any state was finite, then you'll have a positive recurrent Markov chain which has steady state probabilities, which has positive probability eventually of being in any state. So these are bigger concepts which when you do Markov chains, you'll study them. But it's a beautiful example of kind of this idea of null recurrence vis-a-vis positive recurrence, right? So yeah, E of tau with that definition is infinite. In this case, it is finite. And that's because you can build upon the argument I gave you earlier, and I will build upon it in the next slide. But you will not stay between A and B for a very long time. There's kind of a geometric coin flip which is making you go out of this thing. And geometric coin flips have finite expectation. So you can build an argument of that sort. I mean, that's the intuitive content at least. But in any case, let's assume this for now. So now we can apply dominated convergence theorem. So then you get E of m tau is equal to E of m1, right? Which is 0. Because E of m tau is equal to, E of m n min tau is increasing to E of m tau. That you agree? Right? And this is same as E of m0 or E of m1, E of m0. These are all the same numbers. So it's a very funny kind of thing. All of these are same numbers, they're converging to something. That must be the same number. Yeah. It's just a nice way to prove. Go ahead, Gary. It need not be a stopping time, but you can say a lot about it if it's a stopping time. Yeah, if you look in the future, then things kind of change. I mean, if you're counting cards, well, I mean, the counting card is not looking in the future, but in any case, if you have a fixed game, then something where you look ahead, not a stopping time. I mean, last time we gave one boring example. Well, we gave one boring and one somewhat interesting example of stopping time. One was the last time you hit level B. So suppose I'm looking at, so stopping tau is equal to supremum. I should have a better example than this, such that SM, or let's make it somewhat easier. M less than equal to 1000, such that SM is greater than equal to some level A. So last time you were above A up till 10th, up till 1000 steps. So if I tell you that the answer is 900, I need to look at the sigma algebra till 1000 to say that. I need to look in the future. This will, yeah, it will not be a martingale. That you'll have to do case by case basis. Yeah, I mean, there's no crisp kind of answer I can give you. Yeah. I mean, they're not so interesting either. So in that sense, I don't think people have worked hard to develop a crisp. If you can motivate them, then I guess one can think about these. What's that? I mean, all these guys, I'm assuming S0 is equal to 0. Okay. So then S1 is same as expected value of S1 is same as expected value of S0. That remains 0. Right? Because S1 square is going to be expected 1, and then I'm subtracting 1. All right. So now that we have this, then you have A square P of S tau equal to A plus B square P of S tau is equal to B minus E of tau is equal to 0. Right? That becomes a vehicle to get hold of E of tau. And just up to substitute values, you get E of tau is equal to A times B. Right. Okay. Now, why was A tau less than E of tau less than infinity? Let's just show it for now. Huh? Shouldn't have to take my word for it. Okay, so what we said last time was that probability of tau greater than equal to n times A plus B is less than equal to A to the power n. Because in A plus B steps, I have a clear path which is going to make me get out of this band. Yeah. Oh. All right. So there's a clear path which tells me ki, okay, at least with probability 1 minus A, I would have stopped. Hmm? Yeah, let me just make sure I say this correctly. No, hold on. Let me just give me 1 second. If I mess it up unnecessarily. With probability 1 by 2 upon a raised to power a plus b, in a plus b steps, for sure I would have stopped. Right? So with this probability, with this probability, this is a upper bound on the probability I would not have stopped in a plus b steps. It's an upper bound. In a plus b steps, for sure I'll stop with probability 1 by 2 to the power a plus b. Because I'll just go in one direction, either above or below. I mean, that is guaranteed, right? So then with at most probably 1 minus 1 by 2 to the power a plus b, I would not have stopped in a plus b steps. And then I would not have stopped in n times a plus b steps with at most probability a to the power n. I just need something geometric. I'm just trying to prove something finite. I'm not being very nitpicky here. So you're with me on this, right? Now, expected value is given as follows that, for non-negative integers. How do we prove this?
Counter differently, right?
That's right. Just write probability tau greater than equal to n as a summation tau equal to m for m from n to infinity. And then you kind of just change the order of summation and you get the result. Right? It's just because in this, I'm counting probability tau equal to 1 once. I'm counting probability tau equal to 2 twice. So and so. It's very clear. So this is another representation. So now I just need to bound these quantities and I can just do this as follows, right? Because this is an upper bound on the probability that tau is greater than equal to n times a plus b plus 1, n times a plus b plus 2, all the way up to n plus 1 into a plus b. Right? When as I increase this guy, my probability only reduces, right? So I can upper bound it by this probability. So now, because I can do that, I can get this upper bound on this term right here. Is this clear? I'm just counting, a plus b steps at a time. So I look at a plus b steps. I take my first term as an upper bound on all these probabilities. I multiply that by a plus b. And then I look at next a plus b terms. This is just because probably tau greater than equal to 0 is 1. So first a plus b steps, I'm just bounding by a plus b. I mean, I'm rich. I just need to show this is finite. So you get the idea, right? So these geometric, whenever you see a geometric intuition, one can come up with these proofs. Yeah. I just need a upper bound. Everybody with us so far? Parin, what's troubling you?
The 1 by 2 a plus b.
Yeah.
If we're going in one direction, so shouldn't it be 1 by 2 to the power a or 1 by 2 to the power b?
So I'm just being large. I contain multitudes. I had to plug that in somewhere. Okay. So anything else or that's fine? Yeah. Okay, so now let's just state the big martingale stopping time theorem. It's kind of just putting everything together. So let Mn be a martingale on my space here with the filtration calligraphic Fn. Tau is the stopping time. M0 is equal to sum C. Then EF M tau is equal to EF M1. Because that's a big result. And the import of the result is that you can't beat the casino by being clever about your stopping strategies. Right? No matter what you do, on an average, your rewards are going to be same. But already I've told you that there is a strategy where you can beat anybody, which if you keep on doubling, so we have to assume that away. We can't allow such strategies to occur. But other than that, for a large number of strategies, we have the result that you can't really improve by being clever about when to stop. All right. So one is which strategy? The way you actually can beat the casino? I guess so. I have to think about this.
Practically, you can say,
Yeah.
you will never do that because you'll run out of money sometime or the other.
Right.
But is there a way to, like, when you're saying you're assuming something away, what is this formal assumption you've made?
I mean, I don't know. You can just say stop when you made at least 1 rupee. So all stopping times with those properties, which are finite. That would character.
Expect, so some you want to expect stars finite, we just want those them. Is that the question?
So let's see exactly what's your question now.
So my question is, when you said we can assume certain things away,
Yeah.
how do we characterize them formally? Is it that you say we'll only take towers where the expectation of tau being infinite is zero?
So let's see these three assumptions. In the sense, one, I'm assuming also that the amount of winning in a game is bounded. In that example which I gave you, the amount of winning was not bounded. That's also a problem. Or stopping time can be, expected stopping time can be infinite. So I'm assuming those things are finite. So these are sufficient conditions. You somehow want necessary and sufficient conditions, or maybe conditions in the other direction. That, but this goes a long way. I mean, how do we assume that way? Let's at least see that. So first is the easiest case. Tau is bounded almost surely. That means there's a constant k, and tau is less than k with probability 1. Right? In that case, the result just follows. So because, how does it follow? Because, I have E of m1 is equal to E of mn, and as my n becomes, I guess I probably need this only, right?
So we just need m and tau converging to mp almost already, and that we get from.
Yeah. I mean, in this case, I don't even need that. I just look at this quantity here. And when I take my n to be bigger than k, when my n min tau is equal to tau.
Not even almost already, but.
Yeah, I don't need that either. Yeah. But my tau is bounded, so, I already have tau being finite. Okay, so this one is very easy. Second one is your mn itself is bounded. Your martingale itself is bounded for all n, and then probability of stopping is finite. It need not be bounded, but its probability of stopping in finite time is 1. So in that case, you can see that just by bounded convergence theorem, you'll get your result. Because your mn will converge to, sorry, I forgot to remove this. This is just typo from latexing somebody's notes. This should be just this. Right? So mn will converge to m tau. Mn is uniformly bounded above. It's dominated. So by bounded convergence theorem, I'll get this quantity right here. Yeah. Yeah.
So any one of your product or all.
So expectation of E of mn or E of m tau? If any of one of these things are true. Any one of these things is true. Yeah. Yeah. Sorry. If any one of these holds. This is one of those things which I just won't write, but I expect you to ask and figure out. Okay, so this is now, you can just go back and use the argument that we did earlier. Mn min tau is bounded. Mn min tau is converging to m of tau. Dominated convergence theorem. Expected of mn min tau is a constant, and that's converging to E of m of tau. So E of m of tau must also be equal to E of m of 1. So this was easy. The interesting one is the last one. Suppose now your increments are bounded. Yeah?
When you say DCT here, it's bounded.
Yeah, BCT and DCT.
Use another one.
Yeah. Okay, now we have increments which are bounded. And we want expected time to stop also to be finite. So we've increased our requirements on the stopping time. So then how do we prove this? So can one try and see how might we prove this? It's a little bit harder now, right? To prove that E of m tau is equal to E of m1. Because now the increments are bounded, so we have to be careful how we use dominated convergence theorem. So in tau steps, how much reward could you possibly earn?
Tau and something of those then. It is tau k.
Tau times k, right? Tau times k. Now, but tau is a random variable, but it has finite expectation.
So
That's enough. You can see it here, right?
then dominant conversion.
Then dominant conversion, yeah. So you can write your Mn. I should have a thing here. Right? Mn can be written as follows. I'm assuming here, I guess, M0 is equal to C. That's fine. Yeah. So because of this, I have my M tau is less than or equal to C plus K tau. ठीक है. C is my value at M0. Yeah. Okay. So you can use dominated convergence theorem and make everything work. There are one or two missing steps here that I'll just ask you to fill them up. But basically, this is going to help. Okay. So now let's make this fun. Let's do some magic. And this is really magic, huh? Okay. Just repeat after me. Abracadabra. So alphabet symbols are picked independently. Each of the 26 are equally likely. Right? How many draws on average till you see the term abracadabra? You see the sequence abracadabra.
How long?
It's 11 thing, yeah. Should be 11.
1 by 26 to the power 11.
Huh? So 26 to the power 11 is what you'd guess, right? It's a geometric experiment. Each time, probability of seeing the sequence starting now in the next 11 draws is 1 upon 26 to power 11. So you expect it to be 26 to power 11.
Geometric.
But that's not quite the correct answer. Because it's not like if I start now, I'll see this or I will not see this. Even if I don't see this,
You still have an option.
maybe I've seen something which will still help me. I've seen Abra, for example, at the end. So it complicates things, right? So it's a difficult problem. If you had to solve it on your own, it will not be that straightforward. You'll have to maybe say, okay, maybe I write a recursion like this, and those recursive equations might have a solution. Martingale makes it very straightforward. Sarvesh, you know the answer. Do you remember it? I guess is the question.
The small ones like head, tail, head, and so on. I've seen this steps.
Okay, yeah.
Carry it.
You're not carried forward, huh?
See.
You've seen it, okay, yeah. Now this, yeah, it's a nice thing. So consider a gamble where a new party bets rupee 1 at each time. So at each time, another party starts betting rupee 1 in the game. If A comes at the bet, the winning party wins 25 rupees, right? So with probability 1 by 26, it wins 25 rupees. With probability 25 by 26, it loses 1 rupee. So the amount it won is a martingale. It's a fair game. Now, if it does win, then it has 26 rupees, 1 rupee it had in its pocket, 25 it won. It bets all those 26 rupees on the next character B. Again, it wins 25 times that. So if it wins, it will have 26 square amount of money. If it loses, it lost at 1 rupee, the game over. Right? So this guy will go on. So any guy, if abracadabra does not come, will lose 1 rupee. And we'll observe this game till abracadabra comes. And then one guy who's won it at that time would have won 26 to power 11 rupees. Would have 26 to power 11 rupees with it, with that person. He started with 1 rupee bet, so he won 26 to power 11 minus 1. Right? So,
On A, I'll put a 1 rupee bet.
yeah,
I get 25 minutes paid if I win.
if you win, yeah.
So now 25 minutes.
Now you have 25 plus 1, the 1 rupee bet that you made.
Okay, I won 20. That's okay, 26 now.
Yeah.
I bet all of this there.
That's right.
Now I got 25 into 6.
So now you got 25 into 26 if you win.
But I already had this.
26, so you have 26 square. So if you lose,
I'm just betting 26 to power n.
yeah,
That equals that.
that's right. If you lose, you've just lost 1 rupee. You started at a particular time and you lost 1 rupee. If you win, so we'll stop all of this, we'll stop this sequence of games at the time when we finally see abracadabra. Then one guy who started at that time tau minus 11 step actually won 26 to power 11. Almost all these guys up till now have lost money, but not everybody's lost money. So what else is going on? When first guy saw abracadabra, first time we saw abracadabra, has everybody lost money up till now?
What mean everybody? There's one person.
No, there's not a one person. Every time I'm starting at time one person makes a bet, either it loses or not, goes away. Second time period, second person makes a bet, and lose or not continues. So at every time there's a new person making a bet.
Everyone would have lost.
So it has everybody but one lost? Think about this.
Yeah, because if he won, then everyone, he only came because everyone else lost.
This is what we've seen. The guy who came at tau minus 4 time, he's still in the game. He's seen abra so far. He put 1 rupee, he has 26 to power 4 rupees with him.
There's no lost.
Huh?
But he joined at tau minus.
No, every person is joining, a new person is joining at every time.
Not given that you've lost.
Yeah. No. Just joining regardless. That's how we set the game up. That's the right way to set the game up. That's where you would go wrong if you were to think on your own. Setting the game up right is a problem. It's not so straightforward. So this guy is won 26 to power 4. Anybody else? We want to see the entire sequence exactly in that order.
Then everybody before we should also lose, right? Because we're not, that sequence is now gone.
That's true. Yeah, they would have lost. But now so all I'm saying is let's carry on that way. People kept on losing. And we stopped when we saw a complete sequence of abracadabra. Right? So now my question to you is, who all have, one guy is obviously won 26 to power 11 minus 1. As anybody else who's also in the winning right now?
Not that.
No, why 26 to power 10? That guy is, the guy who started 10 steps ago, he saw B, he lost. Yeah. The guy who started 9 steps ago saw R, he lost. The guy who started 8 steps ago won the first one but lost the second one. Yeah. So the guy who just came in has bet on A, and that guy is also won. The guy who came here has won 26 to power 4. This guy's won 26, and the guy who came here has won 26 to power 11. Yeah. That's the whole point, yeah. It's hard to come up with a good word, but as he said, heads, tails will also do it. But that's less fun. This is magic. Huh? So now what's... No, but why? I mean, abracadabra, we stopped. Abracadabra has happened, we stopped. Now somebody had started betting 4 steps earlier, right? When that person bet, the first outcome was A, the person won. Then that person took 26 rupees and bet on B, and again won. And then that person took 26 square rupees and bet on R, and again won. And so that person has won 26 to power 4.
I now, okay, so I can just wait till I see the next part. Is that?
The game is very clear. At every step, there's a new party which starts betting 1 rupee. If A comes, then they'll increase their bet. If A does not come, they lose. If A comes, the next time they'll bet on B. If B comes, then the next time they bet on R, so on and so forth. So that's how each player is going to play.
Each person is trying to build their own abracadabra sort.
That's right.
What
That's right.
What has happened?
Nothing of that sort. Yeah. Absolutely. So then you're asking yourself, who's in the game when abracadabra finally occurred? We have 3 winners so far.
And everyone before this has already lost.
Yeah. So the total winning, so
Candidates.
hmm?
I mean, you have one winner and two candidates.
Yeah, but they won something so far.
Sure.
Yeah. So the total amount that's won so far is 26. So winning over all the people at any time is a martingale process, not one person who's kind of losing, all the people. And the overall winning is this much, or there should be four. Sorry. See again, planted error.
The first person is 125.
What's that?
The first person is 125.
No, so that one has gone in the T step, right? T is absorbed at one, right? So every 1 rupee is going into T.
Yeah.
So first one has won 26, the guy who's won has won 26 to power 11 minus 1. On the fourth step, he's won 26 to power 4 minus 1. And the last guy has won 26 minus 1. Everybody else is minus 1.
So I understood what the game is.
Right. Let me just write the picture down, then let's come back to this. And now here you have your Abra. Cadabra. Right? And now this guy has won 26 minus 125 rupees. This guy has won 26 to power 4 minus 1. This guy has won 26 to power 11 minus 1. All the other guys have lost minus 1. So this is 3 guys here. So they won whatever minus 3. And the remaining T minus 3 guys have lost 1 rupee. So total losses are T, the way you count them, and winnings are 26 to power 11 plus 26 to power 4 plus 26. So that has to be equal. So that tells you the expected value of time. In expectation, that has to be 0, right? It's a martingale. So you get the following result. Right? So you can see it's a nice result. And once you've seen it, it's fairly cheaply obtained.
Actually, that would be 610.
I mean, you'll have to look at the sequence. So suppose I tell you H, H, T, T, H, H, H. So then you have to see. So when you stop, it'll be H, H, T, T, H, H, H. That's when you stop. And then these two are still in the game. The last two are still in the game. Right? Nobody else. Huh?
Prof, just one question I have.
Ah.
Shouldn't this be T minus 3
Also
because
sandwich.
it's good. It shouldn't be T minus 3 because
No, I mean, just because other guys' winnings are 26 to power 11 minus 1, 26 to power 4 minus 1, 26 minus 1. So those minus 3 from there I've added to T minus 3.
wait, if it's minus 1, then it should be minus 6, no?
No.
Oh, okay. I
Minus
see.
1 always. It's
Okay,
minus
yes. Okay. Sorry, yeah, you just said that.
the calculation one has to do. Yeah.
Yeah.
Loses one.
That's it. If you stop, you lose 1. And anytime when you're in the game, in the nth step, your winning is 26 to power n minus 1. Because your money you hold in your hand is 26 to power n. And 1 is, that you started with. Winning is minus 1 of them. All right. Dhruvan, see you soon. Okay, guys. So let's now talk briefly about sub-martingales. Yeah?
Minus 3 minus 3 in some sense, not minus.
That's what I just answered right now. That was it. Your telepathy is not working very well. The force is weak. Okay.
What did you answer?
Well, the answer was the 3 people who are winning. They are winning 26 to power 11 minus 1, 26 to power 4 minus 1, and 26 minus 1. So, yeah. Okay, let's talk about sub-martingales. So sequence of random variables mn. This is an easy thing, right? When you define martingales, somebody should ask immediately, why not have an inequality and define something more general? So we'll call it a sub-martingale if on an average you're increasing. So it's an unfortunate definition. It should have been called super martingale because on an average you're increasing. But this is called sub-martingale, and if on an average you're decreasing, it's called super martingale. There's a reason there's a mapping to harmonic functions where this becomes a more natural definition. But even Doob, who came up with this, thought that he had blundered by making this definition later. This is, and somehow, we like to follow, so we're following, so nobody changed it. So anyway, so this is called sub-martingale. On an average, you're increasing. So
When it's more in the sub.
then when it's more, it's sub on average. When it's less, it's super. All right. So this is clear, right? The definition. So I'll just prove this very nice result on sub-martingale inequality. There's an equivalent result for super martingale, which I'll tell you what that is, and that's even more interesting. But that's more interesting in the learning theory world, in the testing of hypothesis, confidence interval world. Sub-martingale inequalities are used more for kind of proving convergence of results. But right now, I'll just give you a flavor of it. If we need these things more, I'll come back and maybe prove more results. But this is a nice result. So Mn is a non-negative sub-martingale, right? Mn star is the supremum of this martingale in n steps. Right? It's just the maximum of the martingale so far. It's all loops, yeah. So super martingale inequality is Wheels, Ville. And even now people say it's interesting stuff. Maybe Sarvesh knows more about this. But apparently Wheel talked about this martingale stuff earlier on, and Doob happened to see something from there. And that might have, it doesn't take much to get inspired and motivated by other people. So Doob may have gotten some of the ideas from here. But it's such a fascinating topic that one worries about, that one, talks about these things. So the point is this: we know that in Markov's inequality, right, you'll have Mn star here. I'll get this right someday. If we were applying Markov's inequality, we'll have this thing, right? That's greater. That's greater, yeah. So the beauty here is that you get this result. Just E of Mn. Right.
Just Markov, not like.
It's more than Markov. This is more than Markov, right? I've got Mn star inside and Mn outside.
Star is greater than.
Yeah.
No, because Mn star is greater than Mn, right? Expectation of Mn star is greater than expectation of Mn.
That you agree, right? Because Mn is less than or equal to Mn star. Yeah. So this we knew always. This is a big interesting result. So it's much stronger. Yeah. So the maximum is not increasing that fast.
EMN or EMN star.
Which Emn. The right hand side is Emn. If it was Mn star, that just follows from Markov inequality. Right? And it turns out for super martingales, E of M infinity star even is less than or equal to E of M1 by A. So that's Wheel's inequality. So when your process is on an average decreasing, it never exceeds, chance that it ever exceeds A has this bound, which helps you control things like it never exceeds A. It's very important from that point of view. So this is kind of used in coming up with tightest confidence intervals in estimates, etc. But this is Wheel's inequality. I won't talk about this again unless we need to. Why we did the proof of Markov inequality, right, earlier? Oh, you were not there in this class. Yeah. So the rough proof is x fx dx. That's your expected value, right? 0 to A, 0 to infinity, because it's continuous time. I mean, it's non-negative. For discrete variables, you'll have summation. But you agree that this is bigger than or equal to 0 to, sorry, I'm just. Because it's all non-negative, right? Whatever I'm throwing away is non-negative. And this is greater than equal to A times probability that X is greater than equal to A. That's equal to E of X. So this is Markov's inequality. Right? So that's very cheap. And you get Chebyshev right from here. Right. Okay. So shall we look at the proof of this? It's an interesting proof. Again, it's probably once you're more adept at these things, it's not such a hard thing to see. But what we do is we rewrite this event A as big at set A as union of sets AM, A sub M, where A sub M is just the event that the first time you cross level A is at step M. Up till M minus 1 steps, you were below level A. So M star M minus 1 was less than A. M sub M is bigger than A. Right? Because this is kind of like saying it's kind of like level crossing, right? Your martingale has crossed level A. So then, okay, you can say whether that crossed level A in the beginning or at first step or second step or end step. So we've just kind of taken a disjoint union of these sets, and these are my AMs. Right? So then P of AM, because on AM my M sub M is bigger than A, I get this bound. Right? In the integrand, instead of putting 1, I put in something greater than equal to 1, M sub M by A. On AM, M sub M is bigger than A. And because I have a because I have a sub-martingale, on an average, this is increasing. That you have to show. Huh? This is exactly the same proof that you saw in martingale, but with inequalities. But you should have that E of M I of A is less than equal to E of M N I of A whenever A is in Fm and N is bigger than equal to M. What's that? Sub-martingale, right? So it's increasing, huh? Sub-martingale is increasing, yeah. Okay, so this requires a proof, but this is the kind of stuff Anirban will give you as homework. Okay. So this should be true because this is an inequality we saw for martingales. The same argument show you this to be an inequality for some martingales. But yeah, so MM is something which integrates, well, not quite, but if it was a martingale, it would integrate like MM, but it satisfies this property. All right, so for that reason, I get this here. That's exactly what gives me this inequality here. Everybody with me so far? Okay. So I have this inequality. Now I'll just sum up these probabilities. These are disjoint. So I get P of M star N greater than equal to A. So very simple stuff, huh? They just do the lines of proof. There's nothing much going on. That's this quantity right here. And that's because Mn is the same. And this thing in turn is less than equal to E of Mn upon A. I kept the setting that if Modi calls, then I should listen to it. Somehow, maybe even the vice chancellor. That's it. Okay, so we get our result, right?
Is this like a discrete type set?
No, nothing discrete. Nothing discrete. Just that when you cross the level, that's a discrete event. You can cross the level at step 0, step 1, step 2. That's yeah. Because I constructed those sets to be disjoint, so probability of the union is union of the sum of the probability. This is just discrete time martingale, but martingale itself can be continuous. Yeah, that's what his question. In the continuous time. In the continuous time, it will not work out. Yeah, that's right. So in continuous time, this is the whole thing. The lot of technicalities goes into kind of somehow reducing the continuous problem to discrete problem. So you take continuous problem, you grid it, you have a fine grid on it, you have stopping times on that fine grid. The stopping times are your kind of tools to, create, discrete systems in a continuous system. Then you get this result, and then you take some kind of limiting result to make it work. We won't talk about those things in this course. But things like what we didn't cover. Hmm? I mean, I'll just tell you these results. I won't prove them.
But it's going to be something like MCD or DCD.
Fatou's lemma, which I didn't do. Yeah, those kinds of things. All those kinds of stuff, yeah. But you can read this stuff. Huh? This is nicely done in Michael Steele. You'll see it there. That's a good book to read for this. And if you really want to, cross your T's and dot your I's, then you go to Casas and Shreve, Brownian motion stochastic calculus. So there all the details are kind of spelled out in Corey. Depth. All right. So we got the sum-martingale inequality, right? Good. How are we doing on time? Good. So we can say that we started the Brownian motion before the midterm break. So now we'll move on to Brownian motion. So any questions so far on discrete time martingales? Now's the time to ask. Okay, so let's go on to continuous time processes. I'll gloss over technicalities, but we'll focus on kind of substantial issues. So BT is now a stochastic process. Stochastic process is again a collection of random variables indexed by time. In this case, time is a continuous variable, right? And now we'll have filtrations as before. So we have the underlying probability space. FT is an increasing sequence of sigma algebras. But again, T is taking values in its non-negative real lines. And we'll call this process B of T to be Brownian motion if it satisfies these following four properties. Filtration, yeah. Yeah, so just that, it just has this.
Quality is greater than S, then you have.
Yeah. It's increasing sequence of sigma algebras, increased collection of sigma algebras, yeah. So it's exactly how it should be.
But no, in some sense, F now, see, earlier you could say that your F is like union of FP.
No, you can still do, you can still take your F. Earlier also I couldn't say this, right?
You could, because it's just countable.
No. Union of sigma algebra, countable sigma algebra is not, union of a finite sigma algebra is also not a sigma algebra. Huh?
No, but then,
So
arbitrary union is also okay.
Smallest sigma algebra which just has all these sets, yeah. But it's much more nuanced than this. Defining random process, defining underlying space. And it's fun stuff to do this because you learn a lot. And a good reference for that is Shiryaev, a book called Probability. Have you gone through it? Yeah, that's a lovely book. Yeah, Shiryaev, Albert Shiryaev. Yeah.
So, F is a countable union of FTs.
No, now FTs are uncountably many. They're uncountably many. So you take the uncountable union, then you take the sigma algebra, which contains all of them. But in reality, it's a more nuanced definition how to make all this work. We're ignoring all those issues. Okay. So we are kind of in the Einsteinian world. So when Einstein first wrote about Brownian motion and its properties in his paper in 1905, he didn't have to worry about technicalities at all. You see Gaussian noise, central limit theorem, you kind of expect Brownian motion to hold. So you just expected it, and then you kind of played with its properties. That was 1905. Before him, I must have mentioned this to the finance class earlier, there was Bachelier in France who was a Poincaré student, and in France, option pricing was quite prevalent. So you had to price options, and then he used the Brownian motion to price options. And there he developed very nice results over Brownian motion, again assuming these properties, but otherwise his results were very rigorous. There's now one of the top conferences in math finance is Louis Bachelier conference. Okay. This is an important property that the increments are independent of Brownian motion. If you look at how much the Brownian motion changes in any incremental time period, T4 minus T3, BT4 minus BT3 is independent of BT2 minus BT1. If the interval T1, T2 is, occurs before T3, T4. So the increments are independent. Whatever happens in those intervals is independent. Now, if you know of Poisson process, this is also true for Poisson process, that the increments are independent. Number of Poisson events that happen in one interval is independent of number of Poisson events that happen in another interval. So it's not a unique property. It comes up elsewhere as well. But Brownian motion satisfies this. Third is, which is very interesting, which Poisson process will not satisfy, the distribution in the increment of size t is Gaussian with mean 0 and variance t. So variance increases with the size of the interval, but it's independent of everything else, independent of whatever happened till time s. Right? So that's property 3. And does that make sense? I mean, what question are you asking? Yeah, it'll take. I know what you're trying to say, but it'll take a while for you to really know what you're saying. But what you're saying is exactly what we'll answer in the next slide. And the last property is very important, that for every omega, B of t of omega, so now I fixed omega outcome. See, what is Brownian motion? It's a collection of random variables, right? You fix a omega, you have lots of random variables. It's just a sequence of, it's a collection of real numbers. That collection of real numbers is a continuous function of time t. It's a function of time t if I fix an omega, but for Brownian motion, it's a continuous function. So the path is going to be continuous. Yeah. Yeah, so what's guiding your intuition is what you're going to cover in the next step. You have to construct your underlying space carefully to make this result work. So what you do basically is you take your underlying space to be C0 infinity. I mean, that's the nicest way to do it. Then it is continuous. This would be called a canonical space. All right. So these are the 4 properties that Brownian motion has. And for the longest time, people assume these properties because you're trying to capture motion of pollen grains, which was obviously it looked like it was continuous. So you didn't have to kind of stretch your imagination for that. And it looked like it was moving incrementally in an independent sort of way. What it did earlier didn't affect what happened later. Huh? Robert Browning, he defined Brownian motion. Yeah, because to explain how pollen.
Was he a math?
No. Biologist or botanist, yeah.
Just a smaller set of bio.
Yeah, so he kind of stipulated these conditions without spelling them out in this manner. But even the Gaussian part is exactly what you're saying. It's actually so many, if you take any interval, just keep on chopping it up. You have so many independent parts, you expect the sum to look like Gaussian because we know the central limits of holes. So it's not surprising that would be that we, and you kind of have a sense that if I double the interval, then I'm summing up 2 variances which are identical. So the variance should become double. if I sum up two random variables which are independent, variance of the sum is sum of the variance. So this 0t is also, it's very reasonable to expect. It's not surprising. Yeah, so people carried on with this, and then in 1923, Wiener first proved the existence of Brownian motion, that you can actually define all of these properties for sequence random variables in a consistent manner. And then there are a number of different proofs of it. I'll just give you a flavor of one most intuitive proof, and that's comes from the random walk. So construction of Brownian motion, I'm just giving you a very large, very high level flavor of it. So again, you consider a simple symmetric random walk as before, right? Sn, as we discussed earlier, is a martingale, and it's also a Markov process. So why is it a Markov process? Let's just discuss this. What does it mean for it to be a Markov process?
T plus one given as T, S T minus one, it's just as T plus one given as.
That's right. So you have to show this property, right? And that's because, if you look at this property right here, this is same as probability Sn plus Xn plus 1 is equal to Sn plus 1, given all of this. That's just same as Xn plus 1 takes value Sn plus 1 minus Sn, given all of this. And Xn plus 1 is independent of everything. So it's same as this property, that Xn plus 1 takes values Sn plus 1 minus Sn, which is also this probability right here. So you get the Markov property. All right. So now, it's important because Brownian motion will also be Markovian. That's why it's kind of useful to know this. And many of the stochastic integrals will also be Markovian. Okay.
That comes from property two, right?
Yeah.
To show it will be
Independent increments. Yeah, absolutely. Absolutely. And property 2 can be seen from a random walk setting. Just look at this new process that we've constructed. How are we doing on time? B and T. Small time goes between 0 and T. So we'll just construct this process, continuous process. Sn of T, lower floor, by root n. Right? Essentially, we've defined this, so T takes values. Let's look at T as a multiple of 1 by n, 2 by n, 3 by n, right? So this is piecewise constant process, but then it jumps at multiples of 1 by n. So that's the wrong way to define it. What you should do is look at the values of this process at multiples of 1 by n and then linearly interpolate. So then I get a continuous process, right?
1 by n, but 1 by n.
By root n.
Using look at the values.
At times as multiples of 1 by n. Because then n times t is an integer.
Yeah.
So it's either S1 at 1 by n, it's S2 at 2 by n, S3 at 3 by n. Right? So it's a well-defined quantity. In between, just linearly interpolate. So you get a continuous process. And now you'll get a sequence of continuous processes. All you have to argue is that the limit is also going to be continuous. Right? There you'll use the fact that in continuous C01 space, under the soup norm, the sequences are Cauchy. So that will help you.
You want that convergence? Oh, soup will tell us it's uniform convergence.
That's right. So you have to show its uniform convergence, and then the limit exists, and and limit will be a continuous function. So all those things I will not do. But that's how one kind of actually gets the limiting object. Sarvesh, who's this by? This proof? Is it by Donsker or? It's Donsker's theorem. Okay. No other name, right? Just Donsker. Okay.
Filling out the space by
क्या करें भाई? Aman. I have to share again?
No.
Yeah. Okay, good. Cool. Right. So, but aim right now is kind of just to give you a flavor of things. So this gives you intuitively what Brownian motion is. It's basically you take a simple random walk, you look at its sample path, +1, -1. You got this whole sample path in your mind now? Now just kind of squish it in terms of time by a factor of n. So whatever you saw at time n now happens at time 1. Whatever you saw at time n by 2 now happens at time half. So you just squish it by a factor of n. And scale it down by a factor of root n. So now you get a picture, right? Now imagine that picture as a function of n. As n increases, that picture becomes more and more jagged.
CNT and
That's the right scaling. Yeah. This will give you the right variance and all that. This is the right scaling. Yeah, exactly. We want it to look like B of t, and we know what B of t is. So now you can imagine this stuff, right? So you can almost imagine a limiting process will exist. That limiting object turns out to be Brownian motion. Okay? And Brownian motion is very nice in the sense it will have continuous paths everywhere, which will be nowhere differentiable. At no point on a set of probability 1, all your continuous paths are nowhere differentiable. So you can't draw them, for example. Have you seen this kind of continuity where functions are continuous but not differentiable? Anywhere. That's right, yeah. Right, so it's a fascinating object. It's been around for more than 100 years, and lots of people have spent a lifetime just studying new properties of Brownian motion. There's always new thing to be said. This is uniform convergence, right? Yeah. That's right. Yeah.
Using simple.
That's right. But if you see Michael Steele, he will tell you how Wiener constructed Brownian motion. And then the
Polynomials of orthogonal polynomials.
That's right. That's right. And then there are two other ways of doing it. I used to know them. I remember one of them through kind of conditionally doing it, but I forget the fourth one. But it's worth kind of catching up on.
And what's used practically?
Hmm?
What do people use practically? Like if I'm going from Apple simulation, what's
I mean, what do you mean? It's a construction of Brownian motion.
so now my point is, I want to do it on my laptop. I want to model.
You want to construct a sample path of Brownian motion.
Yeah.
How do I construct it? I see.
What is the most common one? That the one that's my question.
No. I mean, you'll just generate Gaussian variable, right?
At each time.
At each time, yeah. You take a small delta t, just keep on adding Gaussian variable. That's the easiest way to do it, yeah. Yeah, you don't want to go through random walks and all that. Now, but so what we've done is we've kind of constructed this process here. It's not a single random variable. It's a collection of random variables. Now, I've already told you about a sequence of random variables converging in distribution to another random variable. So now I have a sequence of collection of random variables, collection of stochastic processes converging to a stochastic process. So that tells you that you need the machinery, you need to understand what this means. And it's a very well-motivated problem to say that this converges to that. So you need all the kind of mathematical technology. So a lot of very interesting work went in that direction. But then you can show that this collection here converges to this limiting object, which is a Brownian motion. Right? So that's where a lot of work goes in. But why should that happen? That's very easy to see. Your Bn 0 by definition is 0. Right? For all n. Yeah.
How is that?
So I've not gone into that. I've not defined for you what convergence means of a stochastic process. That needs to be defined, right? Convergence in distribution of a stochastic process. I mean, you could also say that this sequence of this collection of random variables has a probability distribution. That probability distribution measure, let's call it, is converging to the probability measure of Brownian motion. So how are these probabilities getting close? So that's also an issue.
For that, Bn is a good.
That's right, yeah. So yeah, we are kind of just hinting it, but not saying much more than that.
Is it some functional? Like, can't you function into it, then fix an omega.
Yeah.
Now I want to see this function has uniform convergence. It satisfies the properties on the.
So I can take a bounded function of the whole process, B and T, and show that it converges to a function of bounded process, bounded motion. And if I show this for all bounded continuous functions, I'm done.
My point is, I don't want to show this probability. Why can't we just say that, okay, I fix an omega? Now Bn is fixed in that regard, right?
Yeah,
It's a
yeah,
function now.
that's right.
Now I show that as n goes to infinity, this uniformly converges to some Bt of omega.
Right.
And then you're done there.
Yeah, so the BNT converges to BT almost surely is what you're trying to say, right?
Yeah, but
Path in
also
omega by
uniformly
omega.
converges.
Yeah, this process converges and some functions of it also converge.
Yeah.
Yeah, so those are the issues one has to wonder about, right? How to say this in the most natural way.
No, my question is, why do we converge from distribution at all? Why can't you
I mean,
fix an omega just to converge?
so then you have to define Brownian motion on the same space. Right now, we don't even know if it exists. I just told you that Brownian motion should have these properties. I've not told you that there is a Brownian motion which exists.
You don't even know. Okay.
That's right, yeah. Once you know it exists, then you can do these things. Then you can define. Yeah. Right now, I'm just trying to show existence. Right. Okay, but so let's understand why this makes sense. Let's look at BNT4 minus BNT3. We're trying to show the independent increment property, right? That's essentially this quantity right here, modulo the edge effects, which we can accept are going to be negligible. They're going to be easy to show. They don't matter. Right? H कहाँ पे आ गया?
Modulo what?
Edge. EDGE.
Oh.
NT3 plus 1. NT3 need not be integer. So I'll take NT3 to be like, I'll take a floor on it or something. And then I have to worry about that extra thing.
There's some dependent because it might also.
Because what about the t's which lie between 1 by n? They're not multiples of 1 by n. So I have to argue that that difference is shrinking. So those things one can ignore for now. So then if you look at this quantity right here, it makes sense that this quantity is independent of this quantity, right?
As n, you can always get an n large enough such that.
Yeah. That's exactly the point. Yeah. So you have to show that those things are negligible as n becomes large. Right? So hence, asymptotically, these two are going to be independent. Like the increments are going to be independent because there are different random variables which are contributing to them. All right. And then, okay, let's look at BNT plus S minus BNS. That's this quantity right here. And that by central limit theorem, right? I just divide by root NT. I have root NT, in distribution, I can just change the indexes. So I go from 1 to n of t. And then I divide by root of n of t times root t here. So this is converting to a normal 0, 1 variable by central limit theorem. So together it's going to converge to normal 0 t random variable. So this Gaussian assumption makes perfect sense. So you expect this sequence to kind of have those properties. And then you have to verify that the limiting process Bt omega is continuous in each t for each w. Now, limiting processes can be discontinuous also, right? I mean, you can have all kinds of things happening on a set of measure 0. You have to show that you can construct a continuous process, which is a limiting process, which is also a limiting process.
And that is on ground.
That is, no, that's what people did later. In this case, Donsker did. But Wiener kind of, he also did that. But not in this way.
But the point,
the way he approached it, continuity was kind of already there. Yeah. So he just looked at continuous function.
he also did something on the lines of first getting some n, taking n to infinity, showing it converges, and it's a complete space. So that's why this does exist.
I don't want to talk right now. These are things I knew. Maybe you remember it. It's been some, it's like kind of, you have a Fourier series, that kind of series, and then in the limit, like we take a series of finite sums and then you go to infinity, you recover a function. So it's more in that spirit. But let me not comment one. I mean, I can maybe read up and next time I can tell you more. Yeah, I should have read up, but where's the time? Okay. So how are we doing on time, by the way? Yeah, there is no time. Okay, so now what we're going to do is fourth is continuity. So we just assume we won't show it here, but it can be shown. Well, let me just have maybe, let me do this. Maybe at some point I'll have Sarvesh take a lecture and he'll talk about these three Brownian motion things, this different four Brownian motion things, right? Hmm.
In the definition of a Brownian, in the Brownian motion,
Hmm.
you fix omega and dt, omega is continuous. That we are.
Yeah.
But then how do you bring omega in? Like, okay, not to prove, but how does it make sense to bring in omega when you are looking at this constructed version of Bn? What is omega? Like, omega is xi omega.
देखो, omega, what I've done is I've give you a big sample space where I've constructed random variables x1, x2, x3, the whole sequence, yeah. On that sample space, I'm going to construct for you a collection of random variables, sequence of collection of random variables, which will converge to something. And the limiting object, I'll show you, is going to be continuous on every omega, on almost show you. ठीक है, so now there's no lecture this Thursday. And right now, earlier I had said we'll do 26 lectures, but I think the system may allow us 24 lectures. I'll decide, if 24 lectures is enough, fine. If we need one or two more lectures, we'll schedule it after class. But we'll worry about that at the right time. Hmm? No. Is that right? No, there's one. Yeah. So I'll see if we manage in 24, that's fine. If we need one or two more, we'll schedule them towards the end. It's like what you guys do. Let's postpone everything towards the end. Huh.
Which is the best 2 out of 4 time.
Best 2 out of 3. This guy is like, I'll smile and I'll say whatever number I want. ठीक है. So we'll manage in that manner, and if it looks like we need more lectures, we'll create them. And like I said, 24 is what you're going to be graded on. So any extra lectures are, in any case, just covering material. Okay. Okay, so I guess we'll meet after a mid-sem break. Now, let me just say one more thing about your projects. So we've not had that discussion. Guys, hey, Paran, Vishnu, Paran, guys, this project is an important thing. So you have to pick a topic related to probability or finance, but preferably both probability and finance. Get it kind of, you can pair up in one or two people, get the project approved by me. At the end, you have to make 2 presentations. Mid-sem, kind of right after mid-sem presentation. What, 20 minutes? 15 minutes? 15 and 20, 15 minutes. And then finals will be 20 minutes. You'll be judged by, how much of probability and finance content how much kind of maturity you show in your understanding of these things. Right? And it should be broadly relevant to this course. Right?
The presentations are the projects.
That's right, yeah. You'll give a report as well, but presentations are the project.
Already presentations and no projects.
No, that is the project, yeah. And this is a theoretical course. So you read up something interesting, present to us. I would suggest you do something which is of wider interest, so then we'll have these presentations to the whole class. So if you don't do your work, you're embarrassing yourself, not just in front of me, but in a lot of people. We can also have that online. Huh? Preferably. You have the flexibility of changing. It can be conceptual.
What do we prefer? Like, here's the thing,
You're telling us, okay, guys, in this class, we will not be able to cover these credit risk products. But these are the fancy credit risk products. These are the underlying models used to price them. Huh. Was that?
we don't get care too much about right code and about.
That's right, that's right. We don't care about that.
Yeah,
Yeah,
this is
yeah.
only read up on some stuff that's not.
Show your understanding, show depth of understanding.
Understand problems.
That's right. If you do experiments, if you show experiment, that's fine too. That's a bonus. Doesn't go against you. Okay. If you say something more through experiment, that's a good thing. It can be, that's what I said, it can be just probability, just finance, but preferably there should be some association between the two. But in some sense, if it kind of meets the criteria of being of wider interest, so that all of us sitting in your lecture gain something, then that's a good thing. That's a good criteria. All right.
How about all the proofs we did not do?
No. I mean, you'll be able to do only a few proofs. You could do an interesting proof, I guess. If you want to prove martingale convergence theorem, won't be enough, I guess.
Yeah, no, it was 2 pages. You first have this notion of
Yeah.
down crossing.
That's right, yeah.
It's kind of speed.
Yeah.
You just build 1 or 2 tools and then it's off the top.